Hey everybody, welcome to your video week 9 lecture. Two topics in metrology that we're going to continue to cover, and that would be angle and surface measurement. This first video will cover the concept of angular measurement. And the first thing we'll define is the term angle. Remember that an angle is really nothing more than a measure of divergence. We're talking about how quickly or how slowly two intersecting features diverge. That's really how we form an angle. And angles are really interesting because when it came to standardizing the angle, many different civilizations went about it the same way, using the unit circle to define the term angle. Keeping in mind that 1 degree is really 1/360th of a full circle. Now, when it comes to metrology, the tools used to measure angles often work with degrees, minutes, and seconds. The reason for this is because we can talk more precisely about a specific angle as opposed to estimating it with a decimal. So coming back to minutes, remember that a minute is 1/60th of a degree. I think of the degree as being the hour. 1 minute is 1/60th of an hour, and 1 second is 1/3600th of an hour. So in essence, 1 second will be 1/3600th of a degree. So if you look at this example here, 30 degrees, 45 minutes, and 70 seconds, in order to convert this to decimal degrees, all we simply have to do is 30 plus 45 divided by 60 plus 70 divided by 3600. Many of you guys have a degrees, minutes, seconds key right on your calculators, and the TI calculators, you can usually input the value first and then hit the key and select the right unit, whether it be degrees, minutes, and seconds. You're going to enter all 3 values, or 2 if you only have degrees and minutes or degrees and seconds, and then hit enter on your calculator. Casio users, you're pretty much doing the same thing. However, once you've entered that notation in degrees, minutes, and seconds, you're going to have to hit that degree, minute, second key one more time to toggle back and forth between degrees, minutes, seconds, and decimal degrees. So just take a moment here and try this. If you want to pause the video, you can. So the solution to this is 30.769 degrees. That is an estimate for 30 degrees, 45 minutes, and 70 seconds. It's really interesting because a vernier protractor is going to use a vernier scale, and that vernier scale is actually defined in minutes, not decimal degrees. So we'll take a look at that in a moment. Now remember, when you're measuring, let's say you're measuring different parts and you're looking at similar features on different parts, in order to reduce the number of variables and using the same reference, you should be using the same side of your protractor, measuring from the same side or initial side of the feature. Try to minimize those variables so that you have less contributors to potential error. So one tool that's used in metrology, precision measurement tool here, would be a vernier protractor. And the vernier protractor is really easy to use, and you can see the different components, your blade, your beam, and your main scale. Here's your dial, and also you have a vernier scale here. So just to take a look at what these look like, you guys can check these links out on your own, but I'm also going to go through them so you can take a peek. Here is an example of a Starrett vernier protractor, and you can see that here. Notice that we read these the same way as we read vernier scales on something like a micrometer or a vernier caliper. Now you'll notice that your vernier scale goes from 0 to 60. And if we look between each main graduation on the vernier scale, there are 3 parts. So if we go from 0 to 15, we can divide those increments by 3, which means that we're working with 5-minute increments. What does that really mean to us? That means if we take 5 divided by 60, that reduces down to 1/12 of a degree. So these vernier protractors are as precise as 1/12 of a degree in this case. So let's come back to the lecture here. Another site you might find useful if you would like to learn a little bit more about using vernier protractors is this one. And what I want you to notice here is that depending on what type of a feature you're measuring, and also depending on whether you're measuring an obtuse or an acute angle, you may actually have to do a little math to work backwards to determine what your true angle actually is. And you can see that here. So these things are very versatile. They can be used in many different situations, and they're pretty beautiful because they can measure internal and also external features. Very easy to use. You'll notice that the blade and the beam here are basically your reference planes in measuring that angle. So how do we read a vernier scale on a protractor? We're going to read it just the same way as we would on a vernier caliper or a vernier micrometer. Notice what we're first going to do is read the main graduations on the scale. Notice here's our 0 on the vernier scale. It's just to the right of 20, 25, 26, 27, 28 degrees. Now what we're going to do is look for the best match on our vernier scale, and we can see that 15 minutes is the closest match. So this angle represents 28 degrees and 15 minutes. If we were to convert that to decimal degrees, 15 divided by 60 is 0.25, so this would work out to being 28.25 degrees. So I hope you like that example, and I hope it's helpful in understanding the use of these tools. So now here's a nice example from your textbook. To learn a little bit more and keep reading, you want to visit section 2, unit 4. Here are some more physical examples of the use of a vernier protractor. It's really easy to use, and notice if you need it, make sure you have a reference plane to build that accurate frame of reference in the use of this tool. So another tool used to measure angles and really to check that angles have been cut properly, or to help us make sure that we have the right angle setting before making a cut, we can use something known as a sine bar. So this sine tool right here is known as the sine bar. And if you look, what we've got here is the sine bar, and this would be the desired angle that we're trying to create. And the way that we actually create or build up this angle is by building up gauge blocks to represent the opposite side of this little right triangle that's formed. Notice that the hypotenuse is the sine bar, and your gauge block buildup is going to be the opposite side of this angle. Hence the name sine plate, because sine of an angle is opposite divided by hypotenuse. Now, these things come standardized. This is our standard, as well as the gauge blocks. And a good example of that would be a 5-inch sine bar. A 5-inch sine bar would be measured 5 inches from the center of cylinder 1 to the center of cylinder 2. They come in standard sizes. So to look at this a little bit more closely, here are some real applications. If we start with the picture we see to the top right here, notice that what we've done is use a sine bar in conjunction with gauge blocks to build up a certain angle. And in doing so, what we're going to notice is that we're actually going to create a horizontal framework. So what we can do, and this image does a nice job of this, is run that dial indicator across that surface to make sure that the work has been cut to the right angle. This is a beautiful tool for in-process work as well. Notice that we can use a sine bar to set up a certain angle so that when we make our cuts, we make our cuts to the right angle. So very easy tool to use. Now, how do you determine how many gauge blocks you're going to need, or shall I say what buildup you require? Well, it's going to be equal to the length of the sine bar times the sine of the angle that you're trying to build up or mimic. It's a really easy application, very easy to work with and very easy to use. What I've included here is a video, it's a YouTube video that does a really great job of not only showing you the use of the sine bar, but building up gauge blocks and checking a calibration report to make sure that the gauge blocks are within specification before use. This video also incorporates the use of wear blocks. So this is a great video. I'm going to include this link in your videos that will be posted in Canvas so you can check it out. I do advise you to watch it because it's a really interesting and practical application of the use of a sine bar. So here's a physical example of the use of a sine bar. Notice here we have our dial indicator set to the workpiece. We've mimicked this angle over here, and thanks to alternate interior angles, we can see that we're mimicking this angle right here. That's going to be mimicked over here. If this dial indicator runs across this and stays at 0, basically the top plane stays purely horizontal, then this angle looks really good. If not, well, we can go ahead and make the cuts that we need to get the right angle and then gauge and check it one more time. And these come in a multitude of varieties. If you've got a larger workpiece, You can use a sign plate. You can also use a compound sign plate. And compound sign plates are pretty awesome because what they allow us to do is measure compound angles. So we can measure three-dimensional angles, not just angles specifically in 2 dimensions. We build up our gauge blocks here as well as here to build that compound angle. So now what you're going to learn a little bit about in the next video is surface finish measurement. So please go ahead and check that video out next. Thanks so much.